Hey guys, here we go. 4.3, part 3, derivatives and shapes of graphs. Last time I told you about one of my favorite little tables, flowcharts here. So this is what we're going to continue on with. Beginning of this section, we talked about where every function is increasing, its derivatives were positive. Where every function is decreasing, its derivatives were negative. Where a function changes from increasing to decreasing or decreasing to increasing is a critical number. Will always happen at a critical number. Not all critical numbers produce local maxes or mins, though, we also saw. Where a function is concave up, its derivatives are increasing. If its derivatives are increasing, the second derivative or the derivative of the derivative will be positive. Where a function is concave down, its derivatives are decreasing, so the derivative of the derivative will be negative. A function changes from increasing to decreasing always at a critical number. A function changes from concave up to concave down always at an inflection point. Not all critical numbers produce local maxes or mins. An inflection point is, by definition, where a function changes from concave up to concave down. All right, so going back to this, we're going to remind ourselves. We ended last lecture with the definition of an inflection point. An inflection point is where a graph changes concavity. I don't like that color. Where a graph changes concavity. So we have our test for inflection points. To test for inflection points, we set the second derivative equal to 0. And we also decide where the second derivative is undefined. These numbers that we get by setting the second derivative equal to 0 or determining where it's undefined are called potential inflection points. They may or may not be inflection points, so they're just potential. I abbreviate from PIP or PIPs. Once we find our potential inflection points, we put them on a number line. We check the sign of the second derivative before, between, and after all potential inflection points. If the second derivative changes sign at a potential inflection point, it will be an actual inflection point. So the best way to see this is with an example. Keeping in mind from our little table, if the second derivative is positive, then the original function is concave up. If the second derivative is negative, the original function is concave down. Or I should say, where the second derivative is positive, the function is concave up. Where the second derivative is negative, the original function will be concave down. So let's revisit this function. We did this, we looked at and we found our local maxes and mins previously. So we took the first derivative. We got 6x squared minus 6x minus 72. Now this is a quadratic function. The second derivative is quadratic. It's never undefined, but we can see that we have critical numbers at -3 and 4, so that was from a previous lecture. And if we look at the graph of this, if we were to throw it into our calculator, it's a cubic function. It looks like this. We would have right here at -3, we have x equals -3. We had found that we had a local max. Right here at x equals 4, we had a local min. What we're looking for today is this point right here in this lecture. You can see that the graph is arched down as it passes through the local max. It's arched up as it passes through the local min. Where it changes from arched up to arched down is called our inflection point. And this is our goal, to find this point. And it's called our inflection point. The inflection point is where a graph changes from concave up to concave down. And we're going to do this using calculus. We're not going to be using the trace function on our calculator. So remember, we used the first derivatives. We had set up a number line. We looked to see where the first derivative was positive and negative before, between, and after. And that's how we determined the intervals of increase or decrease. Again, you can revisit the last lecture. Or maybe it was the first one. So now we're going to talk about how can we find this point right here where the graph changes concavity. So to find potential inflection points, they may not be actual inflection points, but to find potential inflection points, we take the second derivative. So we know the original function was 2x cubed minus 3x squared minus 72x plus 10. We found the first derivative to be 6x squared minus 6x minus 72. The second derivative is what's going to help us find our potential inflection points, 12x minus 6. We see where the second derivative is equal to 0 or undefined. So this is our only potential inflection point. We can conclude that we know this graph changes concavity, and if it does, this is the only place it can. So we can fairly conclude logically, but we're going to show using calculus. This is a potential inflection point. We want to show using calculus that's in fact an inflection point. So what we do is we draw a number line, we put our potential inflection points, and we see how the second derivative behaves before, between, and after. In this case, just before and after, because there's only one. So we're going to take, here's my second derivative right here. We're going to take our favorite number, any number to the left of 1/2. Let's say 0. We're going to plug it into the second derivative. 12 times 0 minus 6. I don't really care what the value is. All I care about is the sign. So 0 minus 6 is clearly negative. So if the second derivative is negative, we know that the function must be concave down on this interval. So to the left of 1/2, when x is equal to 1/2, to the left of 1/2, the function's concave down. Pick any number to the right of 1/2. We'll keep it simple, 1. Put 1 in here, we get 12 minus 6. The result is positive, so my original function is concave up. So it's going to be concave down to the left of 1/2, concave up to the right of 1/2. So we'll just, and in this case, it is, so therefore, f of x, the original function, 2x cubed minus 3x squared minus 72x plus 10 is concave down to the left of negative 1/2, and it's concave up in there, on to the right of 1/2, in the interval from 1/2 to infinity. Oops, sorry. There we go. All right. So if we, again, look at the graph of this, let's take a minute and pop this into our calculator. Y equals, I'm going to do, I don't know, 2x cubed. This might come out kind of funky. We're going to do, let's see how much of this we can see without adjusting our windows. Minus 72x, that's going to be kind of big. Minus 10. Delete, oops. Ah, sorry. 72x plus, oh, I gotta get my other calculator back. I don't like how this one works. I like my old one better. Let's see, 10. My graph, let's see. All right, I'm really blowing that to the 1. Let's just do that. Here we go. All right, what am I not typing in right? All right, I'm sorry. That's why you should always clear before you pop in a new function. All right, let's try this. If it doesn't work, I quit. Ugh. All right, I'm going to go back and we're going to do y equals, I'm going to clear the whole thing. All right, let's try this again. 2x cubed minus 3x squared minus 72x plus 10. All right, this time it should work because I started over. All right, I'm going to go zoom, zoom 6, go up to my standard viewing rectangle. Woo! And it comes to, all right, so we are not seeing much on in here, are we? So now this is when you have to be proficient at using your calculator. So if we go back to see where our local maxes and mins were back in the very first lecture, we can see that it went really low, like probably, I think it was around Let's try this. There we go. Here we go. Yep, all right. So yeah, that's it right there. So it reached its maximum at -3, a local minimum at +4, and it changed from concave down to concave up at actually a half. So like right in here is where it actually changed at a half. Again, you don't want to do tracing on your calculator. You want to do this using calculus. Let's try one more problem. So given this function, let's find everything. Let's find where it increases, it decreases, local max, local mins, intervals of concavity. So we're going to look for everything. So the first thing we're going to do is find the intervals of increase and decrease, thus identifying the local maxes and mins. So here's my function, f of x equals x over x squared plus 1. I think it's easier to leave it in quotient form. It's a lot easier to see where the numerator is 0 and where the denominator is 0. So the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Remember, do not multiply out denominators. Leave it like that. So this is going to be x squared. I'm just going to write it up here. Plus x minus 2x squared. So it's going to be x minus x squared on top. Nope, I'm 1 minus x squared on top. Sorry, all over x squared plus 1 squared. Obviously, you want to be super careful. So the derivative with your algebra, because if your algebra is incorrect, so the derivative equals 0 when the numerator equals 0. So that's when x is equal to positive or negative 1. We'll do the algebra there. And then the derivative is undefined when the denominator equals 0. So here, we can square root both sides. X squared plus 1 equals 0. X squared plus 1 never equals 0. So here we have no real solutions. So therefore, my only critical numbers are 1 and -1. So remember, we're just testing to see where this is increasing or decreasing. So I'm going to draw my number line. I'm going to put my critical numbers on the number line, -1 and 1, and we're going to see how the derivative behaves. We know the derivative is 0 at -1 and the derivative is 0 at 1. So we pick our favorite number to the left of 1, I don't know, -2, and we're going to stick it into the derivative. Now again, here, if you use some common sense, this isn't all that terrible. You can actually plug the values in, or looking at the derivative, notice the denominator is always positive. No matter what we put in for x and square it, add 1 and square it again, the denominator is always positive. So all we're really focusing on is how the numerator behaves. If we pick any number to the left of -1, say -2, we square it, we get 4. 1 minus 4 produces a negative number. So the derivative is negative to the left of -1. So I put in -2. Pick any number between -1 and 1. 0 is a wise choice. We like working with 0. We put 0 into the derivative function. The derivative is at 0 is 1 on top and 1 on the bottom, so it's positive. Then any number to the right of 1, 2, which is going to produce the same result as -2 because we're squaring it, the derivative is negative at -2. So therefore, my original function, remember first derivatives tell us if the function's increasing or decreasing. It's going to decrease to the left of -1, and then it's going to increase between -1 and 1, and then it's going to decrease to the right of 1. So the function decreases, increases, and then decreases. And we have, if it decreases then increasing, we're going to have a local min at x equals -1. If it increases then decreases, we're going to have a local max at x equals 1. The value would be f of -1. We go back to our original function and we stick -1 into the original function. We stick -1 in here, we get -1 over 2. So -1/2. So the value, when it asks for the value, it's always looking for the output. And the value of the local min would be the local max would be f of 1. We put 1 in, the original function. So remember, value is always the output. It's the y coordinate of the local min or max. And then we can conclude from here, f is increasing between -1 and 1, and it is decreasing to the left of -1 and to the right of 1. So that was practice from the beginning of the section. Now let's look at the concavity and the inflection points. So this is, you can imagine, this is going to get hairy quickly. X over x squared plus 1. We found the derivative to be 1 minus x squared, all over x squared plus 1. Ooh, ready to take the second derivative here? Just want to make sure I had that right before we continued on. All right, here we go. Second derivative. Okay, this is where your derivative taking skills are going to come in handy. The derivative of the top, -2x, times the bottom, x squared plus 1 squared, minus the top. Entire top parentheses are essential, times the derivative of the bottom. We have to use the chain rule. The derivative of the bottom, we bring the 2 out front, leave what's inside alone, drop the power by 1, times the derivative of what's inside, all over the bottom squared. All right, now before you go crazy distributing everything here, we're going to see what these two chunks of things have in common. What I see is that they both have 2x in common. So I'm going to factor right from here. So I'm going to pull out, and actually I'm going to use both these negatives. So I'm going to pull out the negative and the 2x. And then I notice they both have an x squared plus 1 term. This one only has 1, that one has 2, but I can take 1 out. So I'm going to take out x squared plus 1, and then I'm going to see what's left. So if I take out the negative, the 2x, and 1 of these, I'm left with x squared plus 1 in this first term, because I had 2, and I only took out 1. Here, well, this minus got pulled out, so that's going to become plus. I took out the 2x, I took this out, so all I have left is the 1 minus x squared, and this factor of 2. So this really isn't all that terrible. And now I clean this up, and I get, all over, be careful, it's the denominator squared. So it's going to be x squared plus 1 to the 4th. Then I'm going to get -2x on top, x squared plus 1, and then we distribute, that's going to be x squared plus minus 2x squareds, and then 1 and 2, so it's going to be, this is all going to become -x squared plus 3, all over x squared plus 1 to the 4th. Now this is the second derivative. The second derivative, where the second derivative is either 0 or undefined, gives us our potential inflection points. So we're going to now look at the second derivative. And again, it's a fraction. So the second derivative is equal to 0 when the numerator equals 0. And without too much craziness, we factored this nicely. So right here, we get x equals 0. We'll make the numerator 0. This is never 0, because x squared plus 1 is always positive. And then here, we're going to solve -x squared plus 3 equals 0. And we're going to get x is equal to positive or negative square root of 3. Add x squared to both sides, take the square root. And then the second derivative is undefined when the denominator equals 0. X squared plus 1 to the 4th equals 0. But this is no real solutions, because x squared plus 1 is always positive, and anything to the 4th power is always positive, so there is no value of x. So therefore, possible inflection points. So these are only possible inflection points: 0, negative square root of 3, and positive square root of 3. So now we have to see how this second derivative behaves before, between, and after. Draw my number line. I'm going to put my pips on it. Negative square root of 3, 0, square root of 3. We're going to see how the second derivative behaves, and then conclude how the original function behaves. So let's get this second derivative down here. Here's the second derivative again, right here. So here's the second derivative. Keeping in mind the denominator is only positive, so we only really need to see how the numerator behaves before, between, and after these points. So I'm going to pick my favorite number to the left of negative square root of 3. Negative square root of 3 I know is less than negative 2, so I'm going to say negative 4 for safety. So if I put negative 4 in here, I'm going to get, this is going to become positive 8. This is positive, and then negative 4 is going to be negative 16, right? It's because negative 4, we square it first, we get positive 16. Negative 16 plus 3 is negative 13, so positive, positive, negative. I know the second derivative is negative to the left of negative square root of 3, so this is going to be concave down. Pick your favorite number between 0 and the square root of negative 3. I'm going to say negative 1. I put negative 1 in here. I get negative 2 times negative 1. That's going to be positive 2. That term is positive. And negative 1 squared, it's going to be positive 2. So this is going to be positive. The original function is going to be concave up between negative square root of 3 and 0. And pick your favorite number between 0 and the square root of 3. 1. I put 1 in. It's going to be negative 2 times positive 1. This is going to be negative, positive, positive, negative. So a negative times a positive and a positive produces a negative result. So it's going to be concave down between 0 and the square root of 3. And your favorite number to the right of 3, like a million. It doesn't have to be that big, but I'm going to just do 4. Negative 2 times 4. It's going to be negative 8. This is going to be positive, so negative times a positive. This will be negative 16 plus 3, so that will be negative. Negative, positive, negative. Give me a positive. Concave up. All right. So now we can make, so these, in fact, all these possible inflection points were actual inflection points. Doesn't always happen that way. If it went negative, positive, positive, negative, then 0 wouldn't have been an inflection point, but that's not the case here. So let's make our conclusion, finish this up, and you can work on some problems on your own. Therefore, f of x is concave up on negative square root of 3 to 0 and to the right of square root of 3, and is concave down on to the left of negative square root of 3 and between 0 and the square root of 3. F has inflection points at x equals negative square root of 3, 0, and the square root of 3. Woohoo! So hopefully those problems will get you through your homework. We're actually going to have a part 4 to this. All right, so stay tuned for part 4.